Okay, let's dive right into this. We're going way, way back. I'm talking about the very first fraction of a second of our universe's entire existence. Now, there's a powerful theory that's supposed to explain all of it, but what if that theory has a hidden flaw? Today, we're going to explore a really fascinating puzzle from the dawn of time and the seriously clever fix scientists came up with to try and solve it.
So let's just kick things off with a huge question, the kind of thing that probably keeps cosmologists up at night. What if the standard story, the one we tell about the birth of everything, is just a little bit wrong? What if our best, most elegant theory doesn't quite line up with what we actually see when we look out into the cosmos?
Right. So the theory we're talking about is called cosmic inflation. It's this incredible idea that in the first sliver of a second, the universe expanded way, way faster than the speed of light. It went from something smaller than an atom to something astronomically huge in, like, the blink of an eye. This is a cornerstone of modern cosmology. It explains so much. But it's got this one lingering puzzle.
And here is the core of the problem, laid out plain and simple. On one side, you've got the prediction from a really popular version of this theory called chaotic inflation. It basically says that this super violent expansion should have shaken the very fabric of spacetime, creating this massive background of primordial gravitational waves. But then, when we point our best telescopes, like the Planck satellite, at the sky, we see a much quieter universe. The signal from those waves is just way, way weaker than the theory says it should be. It's a straight-up conflict between prediction and reality.
So what do you do when your theory doesn't match what you see? Well, you don't just toss it in the trash. You try to make it better. And in this case, physicists look to one of the most advanced, honestly, most mind-bending areas of physics for a fix, string theory. So let's see how this new player gets into the game.
The fix they came up with is called the Gauss-Bonnet term. Okay, don't get hung up on the name. Just think of it like a new secret ingredient you add to the recipe of the early universe. This idea, which comes from string theory, basically changes the rules of gravity at the insane energies that existed during inflation. And its main job is to act like a cosmic brake, slowing down the production of those gravitational waves. It's like a knob you can turn to dial the theory in and make it match what we actually observe.
All right, so we've got our new modified theory. It sounds pretty good on paper, right? But does it actually work in the real world? The first and most important test is to see if its predictions match up with the absolute gold standard of cosmic data from the Planck satellite. This is where the rubber really meets the road.
And the result? Bam, a huge success. When the scientists crunched the numbers, the theory with this new Gauss-Bonnet term passed with flying colors. It perfectly explained the quiet universe that Planck saw. And this wasn't just some tiny, narrow fit either. It opened up this huge, cosmologically viable region. You can picture it like a map, and suddenly there's this vast, new territory where the theory is allowed to exist. For a moment, it really looked like the puzzle was solved.
But here's a really important little detail. This fix wasn't some magic bullet that worked for every model of inflation. It worked great for that chaotic inflation model we started with. But another popular idea, called Higgs inflation, which tries to connect inflation to the famous Higgs boson, it didn't do so well. Even with this new fix added in, it was still strongly disfavored by the data. So right off the bat, this new tool was helping us sort the good ideas from the bad.
So, just when it seemed like our hero theory was home free, it ran into a second, and honestly a much tougher challenge. See, a theory of inflation can't just explain the beginning. It has to gracefully pass the baton to the next phase, the hot, dense universe we call the Big Bang. This transition period is known as reheating, and it is an absolutely brutal test for any theory to survive.
Think of it like a cosmic handoff in a relay race. First, that unbelievable inflationary expansion has to come to a stop. Then, all the energy that was driving it has to get converted into actual stuff, a hot soup of particles and radiation. That's the reheating part. And only then can the hot Big Bang we all know and love actually begin. Forcing a theory to navigate this whole process correctly is like making it run a crazy advanced obstacle course.
And this is where the story takes a really dramatic turn. The researchers doing this work found that this reheating phase acts like a powerful filter. As they say right in their paper, looking at this transition significantly reduces the parameter space. In other words, that easy win from the first test, it was about to get put under some serious, serious pressure.
So remember that huge viable territory we saw on our map? Well, the reheating test basically just erased almost all of it. It turns out that most of the versions of the theory that looked perfect against the Planck data just couldn't handle the transition out of inflation. That vast continent of possibility just shrank down to a few tiny, scattered islands.
The fix still worked, but only under very, very specific conditions. So, after all that, after surviving the Planck data and the reheating gauntlet, where does that leave us? What's the final verdict here? And maybe more importantly, what does this whole journey tell us about how we even search for the truth about our universe? This table is basically the final scorecard. Higgs inflation, out from the very beginning. The version of chaotic inflation with a more complicated coupling, that's now in clear tension with everything we know. The only model left standing is the one with the simplest connection, the linear coupling. It's the favorite, sure, but it's now heavily, heavily constrained. It survived, but man, just barely. And to put a real number on it, this parameter, beta, which is just a measure of how strong our string theory fix is, it used to be able to be a huge number. But this new reheating analysis puts a hard cap on it. The original paper shows it's got to be less than about 1,000. It's a perfect example of how adding more real-world physics really tightens the screws on our theories.
And you know, this really gets to the heart of it. It might sound like a story of failure, right? A cool idea that got whittled down to almost nothing. But that's not it at all. This is exactly what scientific progress looks like. Every single theory that we can rule out, every possibility we can cross off the list, brings us one step closer to the one that actually works. The process of elimination is just as important as any eureka moment.
So, we end on this thought. A potential flaw in our best theory led us to a clever fix from string theory, which passed one test with flying colors, only to be nearly wiped out by the next one. It just leaves you wondering, how many more of these gauntlets, how many more of these cosmic obstacle courses, does a theory have to survive before we can finally say, with confidence, that it's telling us the true story of our universe's very first second?